Okay, so in this video, we're going to review a few key things from the Predicting Circuit Properties quiz. So we're going to start off with just some rules you have to remember and know about circuits. So the first ones are about current. So in a series circuit, current is the same in all components. That's just something you have to know. Whereas in parallel components, the current splits between the components. So some goes to one, some goes to the other, but it's split up. Potential difference is essentially the opposite. So in series components, potential difference splits between the components, so they share the overall potential difference. Whereas in parallel components, the potential difference is the same across all of them. So it might be useful to note that the rules are opposite for current and potential difference. That might help you remember them. And then other thing that we just have to know is how we calculate resistance. And there's an equation for this, and it's this one here, B. So resistance is potential difference divided by current. So we're going to go for option B. Okay, so now we're going to get on to some calculations. So I've got a page in OneNote for this. So before we start looking at the calculations, I just want to illustrate something that I'm looking for. So I did put this in the question, so you're aware of it. But essentially, when we're doing measurements, so we're using a instrument and taking readings, we should always give those measurements to the precision or number of decimal places as the measuring instrument. And we're going to see that in a second. With calculations, it's significant figures that are important. So we give our answer to the number of significant figures of the piece of data in the question we used that had the fewest significant figures. And I'll flag up where that is because that's a bit of a mouthful. So let's have a look at this first one. So we want the current in this circuit. So this is a fairly straightforward question. So we know that R is V over I. We want to calculate current. So the first thing I'm going to do is multiply both sides by the current so we can get it off the bottom line. So we've now got IR is equal to V, and then we're going to divide both sides by R. That will get us current by itself. So essentially, to calculate current, we're going to do the potential difference divided by resistance. So current is going to be 4 divided by 10, uh, and it wants us to give our answer to two significant figures. So that is going to be 0.40 amps. So this zero here is not considered significant. Okay, so significant. So zeros that come before on the left of the first non-zero number are not considered significant, where this is significant because it's to the right of the first non-zero number. Okay, so that's giving our current to two significant figures. Why are we using significant figures? Because we calculated it, we plugged it into equation. Let's actually have a look at the circuit and see how this comes out. So you can see in here, this is actually the circuit we constructed, and you can see our current is correct. Now, because we are taking a measurement here, I give it to the number of decimal places as the actual instrument. So the instrument reads to two decimal places, so therefore I should record the current to two decimal places. Because what we're saying here is the current is somewhere between, it could be as high as 0.05 or it could be as low as 395 amps there. So when we get a current of 0.4, by quoting it to two decimal places, that assigns this range to it. So all of these numbers would round to 0.40 is essentially what we're saying. So that's where we need the decimal places correct, because the number of decimal places tells us about this range of values. So that's why it's important. Okay, so let's move on to and build up the complexity in the circuit. So not too much more complicated. So the first thing, we want the total resistance. So with series, we just need to add together the resistances, so it's nice and easy. So we should be giving that as 20 ohms, and this zero follows a non-zero number, so this is significant. Okay, so we can write our 20 and it's already got the unit of ohms, so we don't need to do anything else. So the current supplied by the battery, so we already did the rearranging part in the last question, so I'm just going to use that. So we have I equals V over R. We've got the total potential difference is 4, the total resistance is 20. So essentially, we're going to end up with half the current that we did last time, 0.20 amps, and it wants it to two significant figures, so I can just write in there 0.20. So the potential difference across each resistor is, so because these two resistors are identical, they're each going to get 2 volts essentially. But we can do the calculation to actually show that. So the equation to calculate potential difference would be current times by resistance. So the current we've calculated is 0.2. The resistance of one resistor is 10. So you can see we end up with a potential difference of 2.4 volts if we do it by this calculation. However, it says it wants the volts to one significant figure, so we're just going to write 2 volts in there. That would be our one significant figure answer there. Okay, so let's actually see that circuit. So here we go. We've got our two resistors in series. We can see we do indeed get a current of 0.20 amps. And we've given that to 2 decimal places because that's what the reading is given to. Here, because we're measuring the potential difference, we would quote that as 2.0 volts. Again, 2 decimal places, because that's the precision of the measuring device. If the measuring device gives you 2 decimal places, that's what you should record because it tells you what range of values you have. Okay, so moving on to a parallel example. So again, we have to use our parallel resistor law. So what is that? That's this one. So that's just going to be 1 over 10 plus 1 over 10, which is 2 over 10. And this is the part quite a few people forgot in their working. They forgot to flip it over. So 1 over RT is 2 over 10. So that means RT over 1 is 10 over 2, which gives us a total resistance of 5 ohms in there. And it wants it to two significant figures, so we can just go ahead and write 5.0 in there. The current supplied by the battery, we're going to use our equation that we've been using before. So its potential difference is 4. The total resistance is 5. So you can see that comes out as 0.80 amps to two significant figures. Now the current through one of the resistors, so we can use the same equation. So the potential difference is 4 across all of them. The resistance of one of them is just 10. So you can see we're going to get a current of 0.40 through either of the resistors, so that when we add them together, we get 0.8, which is what we should get. So we're going to get 0.40 amps here. And it was split equally between them because they're both identical in resistance. So the potential difference across one of the resistors, well, that's nice and easy. It's just going to be 4. Because you can see here, we've got our power supply. So the energy is lost across this one. So it must be 4 volts, because if the EMF is 4, potential difference must be 4 as well. So let's actually see that in action. So here is our total current, which we should be giving to 2 decimal places. And again, all of these here, there's 2 decimal places. Our potential difference should be given to 2 decimal places as well, so we should be writing 4.00 volts because it's a measurement, so we should give it to the correct precision there. Okay, so let's have a look at some scenarios with non-identical resistors now. So we've had a series where they were both 10. Let's now look at this with different resistance. So total resistance is going to be nice and easy. It's going to be 5 plus 10 gives you 15 ohms. It wants it to two significant figures, so we could just write 15. That's fine. Current, we need to do the total potential difference divided by the total resistance. So that's 4 over 15, which we can then calculate the current of. Let's see what my fractions are. That's going to be let's do 4 over 15. Gives me 0. 0.2666, blah, blah, blah. But we want it to two significant figures. So we're just going to write 0.27 amps in there. I got a few people rounded that to 0.26 for some reason, but that'd be 0.27. And I don't need to write the unit because we've been given the unit already with our answer. Potential difference across the 5 ohm. So V across the 5 is going to be current times resistance. So the current is 0.2666, blah, blah, blah. And I'm using the unrounded answer. The resistance of that one is 5. So it's basically multiplying that number by 5. So that comes out as 1.333, blah, blah, blah. It wanted to two significant figures. So I'm just going to write 1.3 volts in there. The potential difference across the 10 is going to be current times resistance. So it's going to be 0.2666 times by 10, because that's its resistance. And that comes out as 2.666, blah, 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 which is going to round to 2.7 when we round that to two significant figures, because we're going to round up. Again, a few people rounded that to 2.6. We could also have done 4 minus 1.333, and that would have given us a potential difference across 10 as well. But that comes out as the same value, so it doesn't matter how you get to it. So if you actually look at your circuit, I showed it with me measuring the potential difference across the 5 ohm resistor. So again, with our currents, any current reading in here, we should be giving to 2 decimal places. Any potential difference reading, we should be giving to 2 decimal places there. But we can see our values agree with the simulation. Okay, so non-identical resistors in parallel. So this calculation ends up being a bit more fiddly because we're doing 1 over 5 plus 1 over 10. So we're going to have 2 over 10 plus 1 over 10 gives you 3 over 10. So that means that if we flip both sides, we're going to do 10 over 3, and that's going to be 3.3 blah, 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 blah. It's got to be equal to given to two significant figures, so we're going to just write 3.3 in there. And just to check that answer makes sense, it's less than either of those two resistors, so that matches up with what we'd expect. Again, a few people forgot to flip their thing over at the end, so I got a lot of people writing 0.3 as the answer to this one. You have to remember to flip it over because we want to know what the total resistance is. To get our current, we're going to do the EMF, which is 4 volts, divided by our total resistance, so divided by 3.333. So let's actually do that. I can't do that in my head. Oh, well, that comes out nicely. So that comes out as 1.2 amps, which is two significant figures. The current through the 10 ohm resistor. So to get the current, we're going to just do V over R. So the potential difference across the 10 ohm is 4. Its resistance is 10. So you can see that that's going to be 0.40 amps there. If we then do our current through the other one, now I'm going to do it this way, but we could equally have done 1.2 minus 0.4. That also would have given us 0.8 amps. But either way you've done it, you should still end up with the same thing, because these two down here should add up to give you this one here. And the potential difference across either of them is just going to be 4. Again, we're giving it to one significant figure because we're doing a calculation, and it's just going to be that 4 value. So if we have a look at our circuit, you can see our values match up. So I've got the 10 ohm at the top and the 5 ohm at the bottom. You can see our potential difference is indeed 4 across that resistor, and all of our readings were given to 2 decimal places. Okay, final one, a bit more complex here. So the first thing I'm going to do is work out what the total resistance of the parallel section is. So we're going to do 1 over 10 plus 1 over 10, which gives you 2 over 10, which means that the parallel resistance is 10 over 2, which is just 5 ohms. And then if we want to get the total resistance, it's just going to be the 10 ohm plus that 5 gives us 15 ohms. Because essentially what we've done with this calculation here is we've said we can essentially redraw the circuit like this here. So we've calculated what resistance we would have to make this resistor over here to replace those two and not changing anything else in the circuit. And that's why we can then add them together to give 15. So we can stick that in there. Okay, so battery current we're going to get in the same way. So the EMF we can see is 4 volts. The total resistance is 15. We've done that calculation earlier, so I remember that that is 2.66 blah blah. So we're going to give our answer as 0.27, the two significant figures. To get the potential difference across the 10 ohm resistor on its own, we're going to do the current passing through it times by that. So that's going to give us 2.66, blah, blah, blah. So we're going to round that to 2.7. Okay, so then it says, and therefore, what is the potential difference across the other two resistors? Well, it's got to be, so potential difference has to be the EMF, so 4 minus 2.666 is 1.33. So we can write 1.3 in there. Because remember, any loop you go around the circuit, the potential differences must equal the EMF. So let's say we've got this conducting pathway here. The total EMF is 4. We calculated already that this here is 2.66. Therefore, across this one must be 1.33 in order for these two to add together to give that one. And I could equally have drawn the loop around this one here. So we could have gone around that way. This one is 2.66 still got to add up to 4, so you know that this one in here must also be 1.33 as well. So we're just following that rule. And then final thing, the current through one of the 10 ohm resistors in parallel. So to get current, we're just going to do V over R. Now we know the potential difference across one of those resistors is 1.33. And we know its resistance is 10, so you can see that that's going to be 0.13 amps. And that makes sense because if we've got 0.13 going through the top one, 0.13 going through the bottom one, those two add together to give you the 0.27. So that makes sense. So let's have a look at that. So we can see we do indeed get this potential difference of 2.67 in here. And you can see our current through the battery is 0.27, which is split equally between here. It doesn't look like they add up to give 0.27 just because of rounding errors that we've made. But you can see that that works. And if I've actually still got this open, so let's go find that. And we can also move the potential difference across here. So this is the one that often confuses people. People are usually happy with that one. But so we can see here 1.33 across there and 1.33 across there. So our circuitry laws work nicely well.